Welcome, everyone. Did you all hear that North Korea had an election on Sunday? The people voted decisively, and they re-elected North Korea's handsome and beloved 31-year-old dear leader, Kim Jong-un. Both chins. And in a sharp lesson for American voters, they had 100% voter turnout. So think of that, 100% voter turnout. That is why they call it the Democratic People's Republic of Korea, because it is completely full of democratic people. Unlike that Republic of Korea south of the border, which is obviously very jealous that North Korea has all the democratic people. So, when you vote in North Korea, there's one candidate on the ballot, but you get a choice. You can walk over and pick up a yes ballot. You get to vote yes or no. You can walk over to a table and pick up a yes ballot, carry it to the ballot box and drop it in. Or you can walk to the table that has the no ballots and walk on over to the ballot box, and if no freak accident happens to you on the way there, you drop that in the ballot box. And, well, guess what? Kim Jong-un was re-elected with 100% yes votes. I have an official North Korean press photo of Kim Jong-un voting for himself and probably everybody else. And according to North Korea's official news agency, this is an expression of all the service personnel and people's absolute support and profound trust in Supreme Leader Kim Jong-un as they single-mindedly remain loyal to him. Eat your heart out, Obama. It's believed that the reason why North Korea has elections at all is because people are required to go home to vote. That's how you get 100% turnout. And this gives the government a chance to keep track of where the dissidents are. But incidentally, this is the same Kim Jong-un who late last year had his 67-year-old uncle and North Korea's second most powerful person dragged by the armpits out of a Workers' Party meeting on television, and later had him executed, not on television. But there was a report in a Hong Kong newspaper, which may or may not be reliable, that says that Kim's uncle Jong and his 5 closest aides were stripped naked and thrown live into a cage with 120 hunting hounds that had been starved for 5 days. According to the newspaper, Jong and his aides were completely eaten up. I hope they had time to cast a vote first. So the politics is over, and now it's time to talk about data structures. I told you guys I was going to talk about more asymptotic analysis today, but I decided to put that off until next Monday and talk about data structures a little bit instead, partly because you need to implement this data structure for Homework 6, which should be available sometime tonight. And it might also help you with Project 2. So what I'm going to talk about is an abstract data type called a dictionary, and then I'm going to talk about a particularly fast way to implement that abstract data type called a hash table. To motivate the problem, let's suppose that you have a set of 2-letter words and their definitions. Now, what I really want is a dictionary for the whole English language, but to keep it simple, I'm going to start with two-letter words. You want to be able to look up the definition of any word very, very quickly. And we say, when we want to do this lookup, that the word is the key. The key you use to look something up in the dictionary, and what you get out is a definition. And we say that that key addresses the definition. So in the English language, there's 26 letters. So how many two-letter words are there? There are 26 times 26 different possible two-letter words. Of course, not all of them are actually words. ZZ is not a word, but this is all the possible words that could ever be, even if we expand the language in the future. So to implement a dictionary, what I'm going to do is I'm going to allocate an array with 676 slots, one for each combination of letters. And then we can store definitions in that array. Now, once I've got that array, if I want to insert a definition into the dictionary, I have a function called hash code. That maps each word, or more generally, each key, to a unique integer in the range from 0 to 675. And then you use that integer to index into the array. And you store the definition there. And so we're going to call each entry in this array a bucket. So there's 676 buckets, one for each combination of two letters, and each bucket can hold a definition. Now I have written a little class for this. I don't want you to spend the time to copy this down, so just look at it for now, and it'll be in the lecture notes if you want to see it again later. I have a class called Word, and there are 26 possible letters and 26 squared possible words. And the important part here is I need a way to map each two-letter word to a number, and each word gets a unique number. So how do I do that? Well, take a look, first of all, at this little chunk of code here. What does that chunk of code do? In Java, every character can be treated as a number. So the letter A isn't just the letter A lowercase a is also the number 65, as it happens. So there's an ASCII mapping, or for extended characters, there's a Unicode mapping that assigns a number to each character. So what I'm going to do is I'm going to take the first, this is the second letter of the word, word.char at 1, and I'm going to subtract A. And what that does is it gives me a number from 0 to 25 that tells me which letter that is. So if I subtract A from A, I'm going to get 0. If I subtract B minus A, I'm going to get 1. And C will map to 2, and so on, all the way up to the letter Z maps to 25. So this is just a straightforward mapping from the letters to the numbers 0 through 25. This is a two-letter word. I want to map each two-letter word to a unique index. So I'm going to treat that two-letter word as if it were a base 26 number. And so This was the first digit of a base 26 number, and so we multiply it by 26, and then we add the second digit. Those of you who went to discussion section at the beginning of the semester might remember your TAs talking about how to convert bases of numbers. Here's one of the reasons why. Now that we have this mapping, so I can map every two-letter word to a unique integer, now I have a dictionary that stores words and their definitions. And again, this is a table which has room for all possible two-letter words. I allocate one array of 676 entries. And now when I want to insert a word and a definition, W and D, then I map that word to a unique number, and that tells me where to store the definition in the table. Then if I want to look up the definition of a word later on, I have a find method that does that. It just takes the word as a parameter and gives you the definition. And this works because it looks in exactly the same part of the array as insert does. Any questions about this? Yeah. What is hash code? So hash code is the method I showed you before. So that method there. So that is the method that maps two-letter words to a number in the range 0 to 675. And so this is where we need to use that, is here and here. Mm-hmm. Other questions? All right, there's a big problem with this, though, which is it works for two-letter words. Maybe you could use it for three-letter words, but English words can get a lot longer than that. So I think English words go up to about 45 letters for pneumonultramicroscopic silicovolcanoconiosis. So that means that you would have to have a hash table of length 26 letters to the 45th power in order to use this method to store every possible English word. And that is far more than the number of subatomic particles in the universe, so you're not going to get that much memory on a chip ever, no matter how good technology progresses. So we need to do something else so we can get those long words. And another issue is it's not just that we can't create an array of length 26 to the 45, although we can't. It's also that there's less than 1 million words in the whole English language. Let's say there's 400,000 words maybe in the English language, or 600,000. Well, that's a whole lot less than 26 to the 45th power. If we want to store the definitions of all 400,000 English words, we should be able to do it with an array of length somewhere in around 400,000 and not, Googleplex. So there are many ways you could implement a dictionary that doesn't take that much space. I'm going to talk about one way which enjoys the same speed advantage as the same data structure I just told you about, and it's called a hash table. Hash tables are the most common implementation of dictionaries, but definitely not the only one. Your TA will probably tell you about other ones. And later in the semester, I'll talk about search trees, which are another way to implement dictionaries. So let's establish some notation. I'm going to use little n, the number little n, to be the number of keys, or in other words, words, that we want to store. And so with the English language, that's about 400,000. And I want to use a table of hopefully not too many more buckets. I'm going to use capital N to be the number of buckets that I'm going to store those keys in. Now, a hash table is a way of taking a huge space of possible words and mapping it to a much smaller number of buckets. So we might have 26 to the 45th power possible words. We're going to find a way to map every possible word, including the ones that don't exist, into this table of buckets. So we have something called a compression function that takes this huge number from 0 to 26 to the 45th power and maps it down to a smaller number that's in the range of the number of buckets in our hash table. The obvious compression function is this. I'll talk about how to improve this a bit later on, but for now, the point is you have a table with n buckets. You want a number that maps you into one of those buckets. So it's got to be a number between 0 and n minus 1. Let's just take the number modulo n, and there we go. It's now in the range from 0 to n minus 1. One little trick I would need to warn you about when you actually implement this is that hash codes are often negative. And the reason I'm warning you about that is because Java has a function called the %sign, which is like the modulo operator, but not quite the same. They're close, but not quite the same. If you apply the %sign in Java to a negative number and divide it by a positive number, the remainder you get might be a negative number. We don't want a negative number after we do our compression function. So if you get a negative number, add n to it, capital N to it, and then it will be positive. So the good thing is that once you run this compression function, now it gives you a bucket from 0 to n minus 1. The bad news is now you can have two different English words mapping to the same bucket. And there's no way to avoid that. It's just a fact that if you want to compress 26 to the 45th possibilities so that they fit in 400,000 buckets, you're going to have collisions. You're going to have places where two different English words map to the same bucket. Officially, this is called a collision. When several English words happen to map to the same bucket after you apply the compression function, that's called a collision. But we have a solution to that problem. The solution is that we're going to design our buckets so that you can store several different English words in the same bucket and several different definitions in the same bucket. And so the method we use for that is called chaining. And it's really simple. It means that each bucket is not just going to be one word. It's not just going to be one definition. Each bucket is going to store a linked list of words and their definitions. So these linked lists of definitions that happen to land in the same bucket are called chains. And so when several words map to the same bucket, their definitions all reside in the same bucket, in the same chain. But chaining creates a new problem. How do you know which definition corresponds to which word? If you have several definitions in the same bucket, you need a way to know which definition is which word. And so the solution to that is that you have to actually store not just the definitions in the chain, you have to store each definition and its word together in the chain. So each list node is going to store a word and definition together. So now that I've described the solution, I want to give you a sense of what it looks like. So this is what a hash table looks like now. I'm going to call my hash table def table, like I did before. And a def table is going to be an array of buckets. And this array could be quite long, so I'm just going to show the beginning of the array. And each entry in that array is a chain of words and their definitions. And some of those buckets might be empty because no word happened to map to that bucket. And some of them might be longer because multiple words map to the bucket. So it winds up looking like a bunch of list nodes, and I'm going to give each list node 2 pointers for a word and a definition, plus a third pointer that will be the next pointer. And then I can store multiple words and their definitions in one bucket. And there might be some buckets that are empty, and others that have stuff in them. So this is what a hash table looks like, basically. And I've tried to draw the distribution here in a way that's kind of realistic. What you'd like in principle is you would like a perfect distribution where every bucket contains exactly the same number of words and definitions. But things never work out that way in practice. What really happens is collisions are somewhat random. You never know where you're going to get them. You never know where you're going to get more of them. Some buckets, no word happens to map to that bucket. So you wind up with some empty buckets. You wind up with some buckets that might have 2 or 3 or 4 items in them. But on average, the average bucket should have about 1 item or maybe a little bit less than 1 item if you want to make the hash table as fast as possible. Are there any questions about this? Yeah. Each node stores both a word and a definition. And there are two ways you could accomplish that. You can actually add an extra item field to each node so that each node has two items instead of just one. Or you can create a new object called an entry, and an entry has a reference to a word and a reference to a definition, and then you store entries in the chains. Question? In short, the speed it takes to access an element depends on how long the chain is that the element is in. So if there's a word in a chain of length 4 and you want to look up that word, it's going to take you about 4 units of time approximately, plus some small constant, to look up that word. And I'll say a little bit more about running time shortly once I've finished laying out how hash tables work. So I want to first clarify what are the most important operations on a hash table, or the standard operations on a hash table. There are 3 operations that are considered really standard, and then most hash tables support other operations as well, depending on the need. But the canonical operations that almost all hash tables will have look like this. And I'm going to use the same prototypes that are given in the 5th edition of Goodrich and Thomasia. So if you have the Goodrich and Thomasia textbook, I'm following their lead here. So they have a method called insert, which returns an object called an entry. What is an entry? An entry is an object that stores a word and a definition. Or, to be precise, a reference to a word and a reference to a definition. That's what an entry looks like. And Goodrich and Thomasia, all 3 of these operations are going to return an entry for some reason. Now, when you do the insert method, what this does is it computes the key's hash code. Once it has the hash code, it compresses the hash code to decide which bucket that word should be stored in. And then it inserts the entry into the buckets list. And when I say entry, I'm talking about this key value pair object, the word definition pair that I drew at the top of the slide. And then for some reason it also returns that entry. So the way Goodrich and Thomasia do it, the insert method returns the same word and definition you just gave it. But now it's wrapped up in an entry object, in case you need that for some reason. The second method is when you want to look up a word's definition. You call the method find on a key, and if it can find the key, it'll return an entry that has that key and its definition. So the first step of find is that you hash the key. And when I say hash the key, I'm using that as a shorthand for these 2 steps. Hash the key means first you compute the key's hash code, and then you compress the hash code to determine which bucket you're going to put that thing in. Now the reason find works is because it looks in the same bucket that insert puts the word into. So we search that bucket, meaning we search the linked list for an entry with the given key. And if we find it, then we return that entry. Now, sometimes we don't find it because you can do find on a word that's not actually in the hash table. And if you search the hash table for something that's not there, well, obviously you don't find it, so you return null. And finally, almost all hash tables support a remove method. And the way Goodrich and Thomasia do this, the remove method, it acts almost exactly the same as the find method, with one exception. It actually removes the entry from the hash table as well as returning it. So it starts the same way. We hash the key, we search the list, and where it varies from find is the third step. If we find it, we remove it from the list. And then we return exactly the same thing that the find operation returns. You return the entry if you find it, you return null if you don't find it. Any questions on these operations? Yeah. I'm using key and word to mean the same thing here, yeah. Now, dictionaries as an abstraction can be used for a lot of things besides English words and their definitions. They have literally hundreds of uses in computer science. So usually we use the term key for whatever you're using to look up something, and value for whatever you're looking up. So normally, in the examples I'm giving here, the key is a word, the value is its definition. But you might use hash tables in Project 2, and then the key will be a game board, and the value will be its score. So English word is to game board as definition is to game board's score. There's an ambiguity that can be handled in more than one way. You might ask, what if two entries with the same key get inserted? What do? There are two different approaches to this. So you can have a hash table act in one of two different ways, and usually you get to decide which one you want. So what Goodrich and Thomasia describe in the textbook is you insert both entries. That means you're going to have two different list nodes in one chain that both have the same word, but different definitions. And that's totally reasonable, because there's lots of words in English that have more than one definition, and maybe they should have separate list nodes. So you can support having multiple copies of the same key, the same word, in a chain. And then what happens when you call find? Well, the way Goodrich and Thomasia do it is if you call find, it arbitrarily returns one of the definitions. You have no control over which one. And the same thing goes for remove. If you say remove this word, and there's more than one definition for this word, it removes one of them arbitrarily. But Goodrich and Thomasia also propose a method named findAll, which can return a whole list, all of the definitions of a word, instead of just one. There is a second option, which makes more sense for some applications. And the second option is whenever you insert a new entry that has the same key as a previous entry, you replace the old entry with the new one. So if I insert the same word into a dictionary twice, I replace the old definition with the new definition. So those are your choices, and with the second choice, only one entry with a given key exists. So which approach is best, approach 1 or approach 2? Well, it completely depends on your application. Some applications will need approach 1. Some applications will need approach 2. For game boards, you probably want to use approach 2 because every game board has only one score. It doesn't change. One thing I should warn you about quickly is when you are storing an object in a hash table, and that object is acting as the key or the word, it is very important that once it's in the hash table, you do not change that object. Because if you change an object that's a key in the hash table, when you change it, its hash code changes too. But the key is still in the hash table in the same chain it was in before, just now it's in the wrong chain. So don't expect hash tables to work if you change a key once it's in the table. Any questions about this? Yes? Well, let's come to the example I drew. Let's suppose that the hash table looks like this, and you change this key so that instead of being pus, now it's evil. Well, evil is not supposed to go in bucket 0. Evil is supposed to go in bucket 1. So now you have an entry that's in the wrong bucket. Does that answer your question? Okay. Yeah. Uh-huh. Well, in practice, it's going to walk through the chain and return the first one in the chain that it finds. But is that necessarily the one you wanted? Well, you have no control over which one gets returned. That's the point. So the running time of a hash table depends partly on something called the load factor. And the load factor is the name we give to little n, the number of items we're storing, divided by big N, the number of buckets we're storing them in. And this gives you a sense of how full your hash table is. It can be more than 100% full because you can store multiple items in the same bucket. If you have 2 items in every bucket, the load factor is 2. If you have half the buckets are empty and the other half of the buckets have 1 item, then the load factor is 1/2. Now, when is a hash table fast? Well, if all the conditions are right, a hash table is really fast. So if the load factor is low, meaning it's below 1, or at least it's below some very small constant, and the hash code and the compression function are good, and by good, I mean you don't get an unreasonably large number of collisions. And there are no duplicate keys stored in the table. Then, all of those things put together, the linked lists are going to be really short. And because the chains are all really short, each operation is going to take constant time. But this is a lot of ifs. So we're going to talk a bit about what makes a good or bad hash code and compression function. And when I say no duplicate keys are stored, the reason I say that is because if you put in 1,000,000 copies of the same duplicate key, like if you store 1,000,000 definitions for the word set, then every time you look through that chain, you have to walk through 1,000,000 things. And there's no way to avoid that. But under the right conditions, hash tables can be incredibly fast. On the other hand, if the load factor is really big, and what I mean by that is that the number of items you're storing is way bigger than the number of buckets. Like, let's suppose you make a hash table with 10 buckets and store 400,000 English words in that hash table. Then you're not going to get constant time. If you think of the number of buckets as being some small constant, then in the worst case, every chain is linear length, and so the hash table operations are going to take order n time. So it's really important, if you want a hash table to be fast, to make sure you've got enough buckets to store all the words in short chains. So the number of buckets should be about the same as the number of words. Later in the semester, we'll do a more proper analysis of this that involves probability theory. But for now, the main idea is make sure you've got lots of buckets if you have lots of words. Any questions about running time? All right, so let me start talking about what makes hash codes and compression functions good or bad. So let me remind you again what the difference between these things are. It goes in 2 steps. Someone gives you a key, like an English word. The first step is you apply a hash code that converts that key to some number, which might be a very, very, very big number. And then you compress that very big number by squashing it down so that you get an integer in the range from 0 to big N minus 1, where big N is the number of buckets. So we're forcing it to fit in the hash table. Well, hash codes and compression functions are hard to do well. They're a black art. I can't give you a scientific way to always create a good one. But I can tell you some things about what works well in practice and what really doesn't work well in practice. First of all, there's sort of an ideal that we're striving for. The ideal is that if we had an ideal hash code and an ideal compression function, that it would map each key to a uniformly distributed random bucket in the range from 0 to n minus 1. Now, when I say a random bucket, I do not mean that it's a random number each time. A hash table only works if a particular key always maps to the same bucket. So I don't mean random in that sense. I mean random as if it had been chosen randomly once and then stayed that way forever. And what randomness ideally would mean is that if you have 2 different English words, the odds of them hashing to the same bucket would be 1 over n, 1 over the number of buckets. So you want independently random distributions of words to buckets. In practice, that's impossible or almost impossible. It doesn't happen, but we try to approximate it. So I want to talk about bad compression functions and bad hash codes, in part because people very frequently get them wrong. And when you get them wrong, the way you find out is you have a lot more collisions than you think you should have, and therefore your hash table is slow. So let's look at some bad compression functions that give you more collisions than necessary. So to give you an example, suppose that the keys are integers, or specifically their type int. And suppose that our hash code is the simplest possible hash code. We're going to map each int to itself. Since we're storing ints, it makes sense to just hash them to themselves. And then the compression function does all the work. So consider this compression function. We're going to compress the hash code by just doing what I said before, hash code modulo n, modulo the number of buckets. And here, let's say the number of buckets is 10,000. All right. Suppose, just for whatever reason, our application only generates keys that are divisible by 4. It never uses any other key because it doesn't have any use for them for some reason. Can someone tell me what goes wrong? Yeah. You're only going to use a quarter of the buckets, that's right. So when you take a number that's divisible by 4, and you take that number modulo 10,000, which is also divisible by 4, you get another number that's divisible by 4. And that means that in your hash table, you might put stuff in index 0, but 1, 2, and 3 will be empty. You might put stuff in 4, but 5, 6, and 7 will be empty. You're only going to use, at most, 1/4 of the buckets. And the other ones never get used. So not only are you wasting space, but you're making chains that are 4 times as long, roughly, as they need to be. Instead of having an average of 1 item per bucket, you're having an average of 4 items per bucket in the ones that are full, and 0 per bucket in the other 3/4 that are wasted. So that's bad. This is going to slow down your hash table because you have to walk through these long chains when you could have had chains that were only 1/4 as long. All right, but interestingly, the same compression function works a lot better if the number of buckets is prime. So if n is prime, then even if the hash codes are always divisible by 4, when you get hash codes that are bigger than n, they will map modulo to numbers that are not divisible by 4. So eventually you will get the whole table filled in. There is a somewhat better hash code. I won't explain why it's better. If you want to know why, see Goodrich and Thomasia section 9.24. But the better hash code actually does a couple of modulo operations and allows you to use a table of any size. So the idea is you take a hash code, you perform some sort of linear transformation on it, multiply it by an integer, add an integer, and then you take it modulo some very large prime number, and then you take it modulo the number of buckets last. And so again, A, B, and P are positive integers. P is also a large prime. And by large, I mean it should be much bigger than the number of buckets you want to store in your hash table. And this works really well. Again, read Goodrich and Thomas C if you want to know why. But one of the nice things about this is if you want a hash table of length 10,000, then it's perfectly okay to do this mod 10,000 here, because you've already done a mod prime first that mixes up the bits enough that if, say, all your keys are divisible by 4, it won't be a problem. You'll still get them well distributed among your 10,000 buckets because of that modulo prime that you do before modulo buckets. And so I'll just restate that. Now, the number of buckets doesn't need to be prime. Question about that? All right, let me move on to hash codes. One thing about hash codes that makes them tricky is that different objects need different hash codes. You're going to have one kind of hash code for strings and a different kind of hash code for game boards because there are different objects that are represented in different ways. But to give you a sense of the difference between good hash codes and bad hash codes, I want to give you some examples of hash codes for strings, one good one and then several bad ones, and see if you can figure out why the bad ones are bad. So again, here's a good hash code specifically for strings, at least for strings that are primarily ASCII letters. You would want to change this up a bit if you're doing serious Unicode characters like Chinese, for instance. So this is a hash code that works pretty well for strings. How do we know it's a good hash code? Mainly because it's been tried out a lot and nobody's found anything wrong with it. That it is a black art, like I said. You can't just look at it and say, oh, that's a great hash code. You can't. You might find out after trying it that no, it's not so good after all. But this is one that's sort of passed the test of time. And one thing I want you to notice is that what we're doing here is we're taking a hash value, we are repeatedly multiplying it by 127, and then adding the next character in the string. So we're going character by character, adding each one into the sum, then multiply by 127, add another character, multiply by 127, which again you should recognize as roughly our method for converting a base 127 number from its base 127 format to the computer's internal integer format. But I say sort of. We're not exactly treating this string like a base 127 number, and the reason we're not is that on every iteration, we're going to do this little modulo operation, and when the number gets large, when the hash code gets large, that modulo operation is going to mix the bits up on every iteration. So it's not exactly the same as treating it as a base 127 number, but mixing the bits up like this is really effective for hash codes. It's mixing up the bits in a way that doesn't really throw information away, and that's important. And that number was chosen partly to be prime. Prime numbers tend to work better here as well, just like in compression functions. And partly to be large. I want it to be large enough so you can have a wide variety of hash codes, but not so large that this will overflow the integer hash value. Question back there. Can I explain how modulo mixes up the bits? Probably not. It's a great question, but I've never figured out how to articulate the answer to that. It's kind of a number theory thing, and I really should think harder about why that is. I really don't have an answer right now, and maybe I'll think about it some more and see if I can come up with something. I don't know, it sort of becomes intuitive if you think about how doing things modulo prime works, but I don't know a simple explanation for it. I'm sorry. Let me now contrast that with some bad hash codes. And I want you to think of why these might not be good hash codes, specifically in the context not just of strings, but in strings that represent English words. So, bad hash code number 1. Let's sum up the ASCII values of the characters. You might recall from a few minutes ago that I told you that the numbers A through Z, the letters A through Z are really numbers in Java, lowercase a being 65, lowercase z being, I think, 90. So what we do is we just treat our characters as numbers, which Java does naturally, and add them all together. So what could go wrong if I do this as a way of hashing 400,000 English words? Yes? Anagrams. So that is an excellent answer. If you have anagrams, words that have the same letters in a different order, they're all going to collide in the same bucket. There's another answer that's important too.
Like words like BC and AD, they some have the same ASCII values, so you're going to have a lot of overlap, especially with words that have, you're going to end up with sort of a bell curve where there's a very small number of words that these sort of at the edges with low and high values and a bunch in the middle.
Okay, I agree with the second part of what you just said, but there's going to be a bell curve where things bunch up, but it's not because AD is the same as BC. It's for a slightly different reason.
You never get the value, for example, of 100, because there's nothing in the range of 65 to 90 that you can
Okay, that's true. You'll never get the value 100 because there's no way you can add numbers together and get 100. But yes? Some letters are used more often than other letters, but that's not actually a problem by itself because that doesn't necessarily mean the distribution of lots of different words will be uneven. Yes? small numbers aren't going to be used very much. You know, that's true, but I'm more worried about the opposite problem, which is, let's suppose you want a hash table of 400,000 English words, so you have 400,000 buckets. How often are you going to get a word whose characters add up to anything close to 400,000? They're never going to come close. It's like most words, it's rarely going to exceed 500. Well, let's say it rarely exceeds 2,000, just to be generous. Even long words, when you add their characters together, you're very rare you're going to get a number more than 2,000. So what that means is all your hash codes are in the range from 65 for the word up to maybe about 2,000. And so if you're bunching up all your words into less than 2,000 hash codes, you're not going to use 400,000 buckets of your hash table. It doesn't matter what the compression function is or how good it is. If you only have 2,000 hash codes, then you're only going to use 2,000 buckets or less. So that means you're wasting most of your 400,000 entry table. All right. Let's try a different approach. Let's take the first 3 letters of a word, and instead of adding them up, which is obviously stupid, let's do what we did at the beginning of the lecture. Let's treat those 3 letters as a base 26 number, and now we have 26 to the 3rd power different buckets, which is a fine number of buckets for storing the entire English language. So what's wrong with this? There will be nothing in the bucket ZZQ. The bucket ZZQ is very lonely, along with a whole lot of other buckets like ZQZ and QZZ. But it's not just that. What happens at the other end of the spectrum? Yes? Yeah, I like that you use the word prefix, because actually pre is my favorite example. Lots of words begin with the prefix pre, for instance. If you look at a dictionary, there are pages and pages and pages of words that begin with pre and nothing that begins with ZZQ. So you're going to get a very uneven distribution of stuff in your buckets when you want as even a distribution as possible. So let's have a third example. Let's go back to the good hash function I showed you before, but let's make one change. Suppose that instead of doing modulo that big number, suppose the prime modulus is 127, but maybe I only have 127 buckets, so that's okay in this example. If I want to use 127 buckets, is it okay if my prime modulus is 127? Is it okay if I take this number here and make it 127 instead of what it was before? Yeah? Sorry, can you say that a little louder, please? There's going to be one bucket that's never used? I think there's a problem that's much, much worse than one unused bucket. Yes? Are you only going to use the 0 bucket? Not quite, because you do add this at the end, and that modulo 127 might not be 0. So we're getting close here, but yes, sir. Yeah, you've basically wiped out all the other characters. So what happens every time you do 127 times hash value plus a new character modulo 127 is that this contribution gets wiped out, and the last character is the only one that contributes to the hash code. So you've unwittingly, by choosing bad numbers, wiped out all of the characters except for one, and you're going to hash this thing based on the last character in the word. So the last char rules an empty kingdom with no other chars to rule over. So what you want is the multiplier and the modulus must have no common factors. For the modulus to work out well. Any more questions about that? Another important thing you often want to do with hash tables, not an important use of hash tables, but an important thing for hash tables to do internally, is to resize themselves when you try to put too many items into them. So sometimes you can't predict in advance how many items you'll have to store. You construct your hash table, you construct 1,000 buckets, and then somebody sticks 400,000 English words into your hash table. Well, that's bad for performance because you don't have enough buckets. So if the load factor gets too big, we resize. And the reason we resize is that we are in danger of losing constant time performance. We don't want to lose constant time performance, so we take action to fix it up. And the best option generally is to enlarge the hash table once in a while. Let's say when the load factor is about 0.75. Now, that's a pretty arbitrary number. I could have picked 10 or 2 or 0.1, and you'll still have constant time performance. But 0.75 means that most of your buckets are going to have only one item, so your hash table runs just about as fast as you could hope for it to run. So if you have the need for speed, this is what you do. Then you allocate a new array. And I strongly recommend when you resize a hash table that you allocate a new array that's at least twice as big as the old one. And finally, you walk through the old hash table, the old array, and you take each entry in each chain in the old hash table and you rehash it into the new hash table. And when I say rehash, I don't mean copy them into the new array. I mean you actually have to figure out what bucket they're going to be in the new array, because they're not usually going to be in the same bucket in the new array that they were in the old array. When you move from a small hash table to a larger hash table, the compression function changes, and therefore the bucket that a lot of the items wind up in also changes. So you have to actually rehash things from the old hash table to the new hash table. You can't just copy them to the same bucket. That doesn't work. There's also an option sometimes to shrink hash tables, the opposite of expanding them. When the load factor gets too small. And probably 0.25 is a good shrinking threshold if your expansion threshold is 0.75. You want it to be no more than a third as large as your expansion threshold. And the purpose of this is just to free up memory so that other processes on your computer can use that memory instead. Now, as a general rule, enlarging hash tables is much, much, much more important than shrinking hash tables. Enlarging hash tables is what keeps them fast when the number of entries explodes. Shrinking hash tables, all that does is save some memory so that it can be used somewhere else, which may or may not matter. Question? Well, does rehashing impact performance is the question. Obviously, there is one big moment where you slow down a lot because normally hash table operations like insert take constant time. Suddenly you have one hash table operation that takes linear time because you have to walk through the hash table and rehash everything. But what you find is that if you amortize that cost over all the different insertion operations you've ever done, the average cost per insertion is still pretty cheap. And later in the semester, I will actually show how to analyze that. Question near the back? Yeah, one thing the hash table should do is that it should actually keep track of how many entries are in the hash table, and know what the load factor is so that it can resize when the number of entries gets too large. So just like a list, you should have a size field that says, I know how many entries are in my hash table right now. And so what's interesting about this is that even though resizing is really slow, you can prove, and we will prove late in the semester, that the average running time per operation is still constant. So again, you can have some insert operations that are really, really slow because they're resizing the hash table. But you can prove that the average running time per operation over the long run is still always constant. And we'll do that late in the semester. Any more questions about this? Let me talk about one application of hash tables that might help you win the tournament, the network tournament. So a lot of Minimax algorithms and game tree-based algorithms use something called transposition tables. And the idea is that it turns out that in a game of network or chess or checkers, from a particular board, there are different paths through the tree that might take you to the same board. So you, as you search down through the Minimax tree, you might find you run into a same board that you have already seen before going down a different branch of the tree. And because of that, if you just run standard Minimax search as I've taught it to you so far, you're going to be evaluating the scores of those same grids over and over again many times. And evaluating the score of a grid can be pretty expensive. You have to look at its children and maybe its children's children and run evaluation functions when you get to the bottom of the recursion, and it takes a lot of time to evaluate the score for a game board. So you don't want to evaluate the score of the same game board twice if you can help it. What is a lot faster is to have a dictionary where you store game boards that you've already seen with their scores. And so if you see the same game board twice, you can very quickly look it up, find out that you've seen that game board before, and just remember its score instead of computing its score at great expense all over again. So we maintain a hash table of previously viewed grids. And this is called a transposition table. In a transposition table, the key is the grid. And the associated value is its score. So remember, a hash table maps a key to a value. So a grid is analogous to an English word, and the score is analogous to its definition in the dictionary. And so having established that, now the way the minimax algorithm modified to use this transposition table will work is that first it checks if the grid that it's currently looking at is in the transposition table. And if it is in the transposition table, that means we've already computed the score for that grid, and the hash table will return the score. However, if we check whether the grid is in the transposition table and it's not there, which is the usual case, well, maybe it's the usual case, then we go ahead and we evaluate the grid score as usual with the minimax algorithm. And then you store the score and the grid in the hash table so that next time you reach that same grid from a different direction, you'll recognize it and you'll be able to look up its score instead of computing it all over again. Now, transposition tables will only help you with a game like Network or Checkers or chess if you are searching at least 3 levels down, because it does take 3 levels down before you can run into the same game board from 2 different paths. And it's important, by the way, after you've finished searching the game tree and you make a move, it's important to empty the table before you do the next move. And the reason for that is because if you're always searching, let's suppose you're always searching to a depth of 4, then you've just searched a bunch of boards and you've looked at boards that are at a depth of 3 and you've looked at their children but you haven't looked at their grandchildren. The boards that are at a depth of 3, you've searched their children to a depth of 1. Now you make a move, your opponent makes a move, it's your turn again. Now you might run into that same game board again in your search tree, but now it's not at a depth of 3 anymore. Now it's at a depth of 1. So you want to search it much more deeply than you did during the previous move. You want to search it 2 levels deeper. And therefore, you need to forget about the old score and compute a new, better score. Yes? So in network, you can encounter the same tree at 2 different depths, but that's usually okay because you're very likely to encounter it at the lower depth before you encounter it at the greater depth. So you'll be able to take advantage of having a more accurate score for it when you encounter it again at the greater depth. The other thing, it's not going to be that common in network to encounter the same board at different depths because most of your moves are add moves. It's only when you get to the step moves that you can actually encounter the same board at different depths. One thing I want to add here is that you do not need to do this to get full points on Project 2. So this is not a necessary part of Project 2. However, if you want to win the tournament that's going to take place about 3 or 4 weeks after the Project 2 deadline, then implementing this will speed up your machine player and improve your chances of winning. Any more questions about this? All right, one moment. Out of paper here. All right, that is everything I have to say about hash tables. I want to spend the rest of this lecture very quickly going over a few really simple data structures that you should know the names of. And those are stacks, queues, and what are called decks, double-ended queues. So I'm going to talk about a stack. You already know about the program stack in Java, because I've told you about it. There's also stacks that you store explicitly as a data structure, which are very similar to the program stack in Java, except that these stacks are totally under your control, and the Java program stack is not under your control, really. But a stack is another way to store the same kind of information. Now, stacks are nothing new. Stacks are just lists. In fact, a stack is a crippled list. It's a list with less capability than a typical list. So why do we even care about it? The reason why I want to talk about crippled lists today is because the specific ways in which certain lists are crippled tells you something about what algorithms that use stacks and queues are doing. And so that's what I want to go over today. The way that a stack is crippled is that there are only a few operations that we really care about or that are guaranteed to be supported. And those are the following. You can push a new item onto the top of the stack. You can pop the top item off of the stack. And you can also examine the top item of the stack without popping it if you don't want to pop it. And that's all you can do, basically. So the metaphor that everyone uses to talk about stacks is it's like a stack of trays in a cafeteria. You go to the cafeteria, there's a big stack of trays. You can only take the top tray off the stack. If you want to take any other tray other than the top tray, it's going to be a huge amount of work and probably not worth it. So stacks as a data structure emulate that. They assume that you only care about the thing on the top of the stack and you don't even want to look at anything else. And if that's not your goal, then you don't use a stack. You use something else like a full-fledged list. And a stack can grow arbitrarily long. There's usually no limit on how big a stack can get, except for your computer's memory. So here's an illustration of a stack which currently has 2 items on it. And if you do the pop operation, 2 things happen. It takes the item off of the top of the stack, so it modifies the object, and it also has a return value, which is the object that you've just popped off the stack. Or you can push items onto the stack. And when you call the top method, it doesn't change the stack, it just returns the thing on top of the stack. Usually stacks do support a few other little operations like telling you the size of the stack, telling you whether the stack is empty or not. But that's about it. If you want to see what the actual prototypes for the methods of a stack look like, look in Goodrich and Thomassia. It's all listed there. Now, if you implement this in a reasonable way, all of these operations should take constant time. How do you get a stack to have operations that all run in constant time? It's easy. You implement it as a singly linked list. Using just the methods front and insert front and remove front. So I told you that the reason why we would want to talk about a crippled list at all is that when a more complicated algorithm uses a stack, just the fact that it's using a stack tells you a lot about how that algorithm is operating. And I want to give you an example of that so you can see what I mean by that. The thing that stacks are most famous for doing is parenthesis matching. So if you have a string of different kinds of parentheses and you want to know if they're matched correctly or not, a stack is the easiest way to do that. So that will be our sample application. And so an example of that is somebody gives you this. As a string. So I've got several different kinds of parentheses. To be precise, I've got parentheses, brackets, and braces in here. And I want to know if they're all matched correctly, according to the standard rules of English grammar or English open-close punctuation. And so here is an algorithm that answers that question. And the only data structure the algorithm needs besides the input string is a stack of characters. Our algorithm is we scan through the string character by character from left to right. You can use the char at method to look at each character in the string. And then for each character we do something, and what we do depends on whether the character we're looking at now is a left or a right parenthesis, bracket, or brace. So if you hit a lefty, which means either the character left brace, the character left bracket, or the character left parenthesis, you just push that onto the stack. When you encounter a righty, a right brace, a right bracket, a right parenthesis, then you're going to pop whatever is on top of the stack, and hopefully that will be the counterpart to this righty. And so you check that. You check that the righty matches the lefty that was pushed onto the stack. Now, when you do this check, sometimes there's a mismatch. Or sometimes the stack is empty. If you have more righties than lefties, you're going to run out of stack, and then you'll try to pop something off the stack and there will be nothing there. So let's just presume that when we pop something off an empty stack, we get a null pointer back. In either of those cases, it's a failure. The parentheses are not matched correctly. And there's one other situation as well, which is if we get all the way to the end of the string and the stack is not empty at the end, there's still some lefties on the stack that didn't have matching righties, then that's also a failure. If none of these things go wrong, then the parentheses are properly matched, and you can output, yes, it's a match. Are there any questions about this algorithm? I guess I have time to just quickly do it with this string. So let's do it. Here's a stack. First character, push that onto the stack. Second character, push that onto the stack. Third character, push that onto the stack. Fourth character, now we finally hit a righty. So we look to see the top item on the stack. We pop that off and we see if it matches the righty we just got. It does match, so we're happy, but this is gone. Continue moving through the string. There's a left brace, push that onto the stack. There's a left bracket, push that onto the stack. There's a right bracket. So we pop whatever's on top of the stack and check if it matches that right bracket. It's a left bracket, so yes, it's a match and we're happy. And we go on, but that left bracket is gone. Now we have a right brace. So again, we pop whatever is on top of the stack and check if it matches that righty. And it does, so we're happy. That item's gone. We move on. We have a right bracket. Is it a match? Yes, it is. Continue. Now we have a left parenthesis. Push that onto the stack. Right paren Does it match what's on top? Yes, it does. Pop what's on top. Finally, a right bracket. Does it match what's on top? Yes, it does. Pop what's on top. We've now reached the end of the string, so the last thing we have to check is the stack empty? Yes, it is. Therefore, we had good matching parentheses. So I hope that from this, it's a little bit clearer what I mean when I say that the way in which a stack is crippled helps you understand how an algorithm that uses that stack works. If a computer scientist says, here's an algorithm and it does such and such and it uses a stack for this purpose, the fact that you know that you can only access the thing on top of the stack gives you a hint about how the algorithm works. Any questions about this? Another kind of crippled list is a queue. So queues have, like stacks, three main operations. You can enqueue an item at the end of a queue, or the back of a queue. You can dequeue the item at the front of a queue. And you may examine the front item. So, three operations: enqueue, dequeue, front. And obviously this is meant to invoke standing in line at the supermarket. You enter a line at the supermarket at the back, you exit through the front after the cashier processes you. And queues, like stacks, can get arbitrarily long. So maybe this is your queue, and you do a dequeue operation, and that removes the front item, the A, from the queue. And it also, at the same time, returns whatever was at the front of the queue. So, all the obvious operations. I'll give you a sample application for this as well. But this is a much shorter application. The obvious application of a queue is printer queues. So you're sitting in the lab, you print out your project. It goes into a printer queue, and the printer queue processes things in the order that they come in. So if somebody printed their project before you, they're going to get their printout before you. If you used a stack instead of a queue to manage the printer queue, it would be really interesting, because if you printed your project and then everyone else in class printed theirs 5 seconds later, you'd have to wait many hours to get your printout last. That would be very annoying, so that's why we use printer queues instead of printer stacks. And once again, in any reasonable implementation, all these methods run in constant time. A queue is only slightly harder to implement than a stack. A stack can be implemented as a singly linked list. But for a queue, you have to do extra work and also keep track of a tail pointer. so that you can enqueue in constant time. All right, one last data structure, super quick, so you can all go. It's called DEX, and that stands for double-ended queue. In a deck, you can insert and remove items at both ends of the queue. And I think it should be pretty obvious to you how you implement a deck so it runs in constant time for all operations. Now you use a doubly linked list. I don't really know of any compelling application for decks, but I'm sure there is one somewhere. On Monday, I will talk to you about asymptotic analysis some more and how to analyze algorithms. Have a great weekend, and thank you.